carrying on with looking at projectile motion, but now thinking of it with its Cartesian equation. Here's what we came up with yesterday when we were looking at it in vectors, all the different components, and effectively what we have created are parametric coordinates of a parabola. If I look at the displacement equations, that's what we've got. So if I was to recombine them, in other words, eliminate the parameter, let's come up with a Cartesian equation. So playing with the x, we get t is x on v cos theta. Substitute that into the y, and we have a quadratic. Remember, once we've projected, this v is a constant number and theta is a constant number, and g obviously is constant, and so we've got something x squared plus something x. Well, that's a quadratic, confirming that, yeah, we're going to get a parabola. Let's make this look a bit nicer though. We've got sine on cos, we know is tan, and I might, yeah, the reciprocal of cos squared is sec squared. That looks a little bit nicer. In fact, if I wanted it all in terms of tan, I could write it that way. They're all the same, it's just how I've played with the trig identities there to come up with an equation. But there it is. It's a quadratic equation, so yep, we know we'll get a parabola. Now that being the case, instead of using vectors, sometimes we could just use our knowledge about a parabola. So let's go back to these same problems from yesterday. Things like, well, what is the range of the particle? If I've now got the Cartesian equation, what we're really saying is, what are the x-intercepts? What are the roots of the quadratic? Solve the quadratic. And here's our quadratic in the general form that we came up with. If I was to play around with this, I could eventually, there we go, get two possible answers. One would be x equals 0, which makes sense if we're projecting from the origin, and the other would end up being 2v squared sine theta cos theta on g. And you might remember yesterday we came up with something similar in one of our examples. I think there was it was u instead of v, but it was basically the same thing. So x is v squared on g sine 2 theta. If I use the double angle result, I could tidy that up even more. Greatest height. Well, greatest height is the vertex of the parabola. And to find the y value of the vertex of the parabola, we could just go, well, that's minus the discriminant on 4a. For our general one, I go, okay, that's minus tan squared on that expression. Play around with that, and we get v squared sine squared on 2g. What angle does it make with the ground? Now, there's two ways about this. Because the parabola is symmetric, if I'm projecting from the ground, the angle that I hit the ground must be the same as the angle that I've projected from the ground. But if it was some other point, say, okay, with the ground, I could do this with the ground as well, but at any point, essentially, remember that velocity vector was the tangent. So if I find the slope of the tangent, I know the parabola, that allows me then to say, oh, hang on, slope is tan theta, and then we could go and solve it. So the one we looked at yesterday, a ball was thrown with an initial velocity of 25 meters per second at an angle. Determine. Well, now I'll add this in. Let's work out the Cartesian equation of that parabola that we were looking at yesterday. We ended up with x equals 20t, you might recall. So that means t equals x on 20. Subbing it into the y equation that we came up with, here's our equation of the parabola for our particle. Now let's go and solve those problems. The greatest height, well, that's the y value of the vertex, minus the discriminant on 4a. There we go. 45 on 4. So there we could get our 11.25 meters above the ground. The range, well, let's find when it hits the ground. That's how we found the range. So solve the quadratic here, and the roots are 0 and 60. So 60 must have been the range of this particle. Velocity and direction of the ball after half a second. I'll differentiate. So there's the derivative. That will allow me to find the slope of the tangent. Ooh, but after half a second, so I've got to work out where it is. I need the x value for this. So subbing that into our equation for x, and we get 10. So the slope of the tangent is a half. Tan of a half. There's the angle that we came up with yesterday. The actual velocity, well, I'll go back to that v equals x on t cos theta that we came up with before. There's the triangle, because I know that the slope is 1 on 2, so the tan of theta is 1 on 2, hypotenuse is root 5, so I can read off that to get cos theta. X is 10, we just worked that out, there it is up there, and the time is half a second, they've told us that. So velocity is 10 root 5. So using the quadratic or the Cartesian form to solve similar projectile motion questions.